This conference will now be recorded.
ஹலோ சாய்குமார் சார்.
சொல்லுங்க மேடம்.
சார் இப்பயே ரெக்கார்ட் பண்ண ஆரம்பிச்சிட்டீங்களா?
இல்ல சும்மா அழிச்சி பாத்தேன் தெரியாம ஆஃப் பண்றதா பண்ணிருக்கேன்.
This conference will now be recorded.
Good afternoon to all. Today we have our 5th day training on design of electronic circuits for electrical engineers. So again we have our speaker Mr. Ganesh Skandha for delivering the sessions. I'm handing over the session to him. Sir, you can take the session, sir.
Thank you, ma'am.
Thank you, sir.
Yeah, I am Ganesh. I think we all met on the last Monday or Tuesday, I guess. So I couldn't make it on Thursday since I have to go somewhere. Friday on 2 to 3 I had another meeting, so sorry for not making on the two promised times. Now I am here at 3 to 4. We will try to carry over from what we left on the last session. So I was discussing with one of your professors on asking whether a microcontroller class makes sense for a second year, and we think, and we finally decided that it still makes sense because if you want to do any project with an Arduino or any other product from any other company like Microchip or TI or Freescale or any contest for that matter, then you might have to work with a microcontroller. So we think it makes sense to continue the session on microcontrollers. The first thing which I guess you will have this 8051 controller on your course probably in the next year or in the next semester, or I am not really sure, but I think whatever we are doing now might make a lot of sense in your class, and you can start exploring this simulator to learn the concepts of a microcontroller, to see what is happening. So one thing which we thought we'll do was to let you know where to find the simulator, how to download it, how to install, set it up, and things like that. I will spend some time on that as well. I'll do that in between these sessions. But I think we ended the last class with an ADI instruction on ADI 0,32, where we figured out that where we tried to look at the difference between a number system in decimal and hexadecimal and see what a number 32 is, whether it is in decimal or hexadecimal, and when you convert 32 in decimal to hexadecimal, what it will be, and things like that. So I hope the concept is pretty well understood. So I will go to the next set of instruction which I wanted to continue on this class. I hope you remember the class last time. We had a Menti based polling where we looked at the results and tried to understand how much of an understanding you have on the concept, and I think I'll follow the same thing for this class as well. We'll start with an increment instruction. I hope the screen is very visible. So increment instruction increments a variable by 1, so it is as good as adding 1 to it. So that's what this increment instruction does. But the increment instruction, since it operates on only one register instead of 2 registers, for instance, if you do an add, it operates on 2 registers. It has to take the value from A and or not and do this. But an increment instruction can operate only on a particular register and do it. And that way it is quicker than the other one. So if you want to add 1 to it, it will work better if you just do an increment. One thing to remember on the increment instruction is that the carry flag won't be set. You remember what a carry flag is? When we add two numbers and the results cannot be contained within the available space, we set the next bit on the carry flag. So that's what a carry flag is, and we will the increment instruction will not affect a carry flag. So I have a question on Menti to understand the increment instructions. I will go to that. I'll present it so that we can answer it and see how we can take it from there. Uh, okay, so this is the question. So you have an increment instruction on B. There is a register called as B and there is a register called as C. B and C are registers which are looked at as together. So I have taken it as 4 bits. So now the question is what happens when you do an increment X. X is an extended instruction, meaning that it will take B and C together as a single instance and then add one to it. So instead of just operating on B, it will take a combined register. X means extended, so it will take BC as the combined register and try to add one to it. So so I want you to guess what is the output of it. So you have just 2 options. Can you please vote on what you think is the answer for that? The code is 292534 on menti.com. Well, you guys are at it. I will. I hope you should be able to remember the code 292534. I'll probably put it on the chat screen as well, so that I can go to another screen and see if I can let you know where to find. But no, I can do it separately. It's fine. I'll give enough time for you to answer. Then. Is I don't see even a single answer now. Can you see if you can access this? Can someone confirm whether you are able to see the access code and type it, enter there?
The access code and type it, enter there.
So what you have written is visible, sir.
Okay, I don't see.
I don't see.
Students, kindly answer the
Oh, it's
question.
just the voting. Okay, I can see someone mentioning that the voting is closed by the presenter. I will try to go and see why. So can you see if it works now? I can take a mobile and check as well.
Excuse me, sir. In the screen itself, it is displaying voting is closed.
Okay.
Okay.
Okay, ma'am. Okay, I got it, ma'am. I will see why so. Okay. Do you see it now? Yeah, I accidentally closed the voting. Yeah, thank you.
It's now open, sir. It's now.
Yeah, thank you.
Yeah, thank you. Thank you, ma'am. Yes. So I think I have 10 answers. I think I will explain the answer as well so that it makes sense for you, because probably the concept is new to you. There are two registers in this is from a processor called as 8050, not 50. It's from a processor called as 8085, in which there are two registers B and C. So when I do an increment X, it takes both these registers as a together as a single 16-bit register, and then increment the 16-bit register by 1. So if I have B as 0, C as 0, then the value is 0, 0, 0, 0. And if I increment 0, 0, 0, 0 by 1, meaning I add 1 to it, then it becomes 1, 0, 0, 0. So that's how an increment X instruction will work. So it will take both of the combinations together as a single 16-bit register and then operate on it. If, for instance, if I have done a single increment B instead of INX B, then it will take B as a single 8-bit register. B will be an 8-bit register, and then 1 will be added to it. So then it will become 0, 1. So now if I look it together with C, which has a value of 0, when I look at the combined 16-bit of B and C together, then it is 0, 1, 0, 0. So that's the basic concept of how an INX instruction and an INC instruction will differ. So I want to use this quiz as a way to explain this instruction, but I hope most of you have got it right. So please remember to do that. Okay, for a quick example, I have another thing here. So I'll use a highlighter. So the instruction which I'm going to execute is INR increment R0. So it will increment the value at the register R0 by 1, meaning that it will increment R0 by 1. So the value at R0 is now 20. So if I do that, then you can see that R0 has become 21. So I have when I do an increment R0, R0 has become 21. I'll probably I can quickly show that on a simulator as well. I have, okay, the simulator is pretty simple. I will use this place to show the simulator as well. I just downloaded the simulator from the link. I'll post the link on the chat, and then I have this is where I downloaded. I just extracted it and ran this Java library. I think it requires a Java runtime. So as long as you can install that, the simulator should work seamlessly. So yeah, this is that. So now we will do an increment R0. I will set R0 to be FF. So I will run it. So if I run, then R0 has become 0, meaning that when it increments R0, FF plus 1 becomes 0. Hope that is explanatory. I will and okay, I'll do an I'll do this loop, and I'll also do an R0 comma FF comma add a comma R0. I will do this. So then we will see a difference. Okay. So I have FF in R0. So I'm assembled this. Okay. Move R0. Since I cannot move. Okay, we can set it manually. Shouldn't be a problem. Okay. So now I'm going to run it. put something here. Okay, so I'll step through. Now R0 is at FF. So when I increment it, R0 becomes 0. FF plus 1 is 0. You can note that the carry flags are not set. Now I will point R0 to 20. I'm doing it manually. So now if I move A comma R0, oh man. So first this part we have seen. So I'll make it 20 again. Now AC has become 6. Now I'll again make R0 FF and probably will make AC as 1 as well. So now if I step, you can see that AC has become 0 because I added FF to 1. But you could also see that the carry flag has been set. So this was not the case when I did. You can see that the PSW's bit is set. But if I reset and then now R0 is F, I will step. R0 has been incremented and made 0, but you could see that the PSW flags are not set. So that's the difference between an increment and an add instruction. So this is some property which you should remember because this might come as a problem most of the times. You would expect that the carry flag will be set, but it won't be set because that's not very trivial for us. Okay, I'll go to the next. We looked at INX and all those stuffs. Similarly, you have an instruction called as decrement, which will decrement by 1 instead of incrementing by 1. But then all other rules apply. The carry flag won't be set. இது பண்ண சொன்னேன்.
ஃபுல்லா பண்ண தப்பு கண்டென்ட்
ஏப்பா Okay, I lost my internet for some time. Can someone confirm whether you are able to see my slides and things like that? Okay, I hope I can see the slides getting
Yes, sir.
seen.
Yes, sir.
It's visible.
Okay, thank you. So I will do an instruction called as OR. This does an bitwise OR and gives us a result. I mean OR and XOR, all the instructions are very known to us for quite some time. So we have been looking at it from the binary Boolean algebra classes for quite some time. So what is critical on an OR instruction, very different from other instructions which you have seen so far, is previously if you have looked at it, the add or the subtract or any instruction can only be executed on the operand A. So if you remember, this A would have always been the first operand, but now for an OR you can actually do an OR with an A at not as the destination, and IRAM address can be the destination and A can be one of the operands to it. So similarly you can also do it with A, but you can also do it with another location. So that's one thing different on an OR instruction from other instructions. The advantage is that you don't have to move a variable from an external memory to your registers, you can have it there in your RAM and then execute it there itself. I don't have a lot of explanation on how this is going to work. We'll attack it from an example perspective. So there's going to be another quiz. So please open menti.com and be ready. So the question is, I'm going to do an ORL, which is OR logical bitwise OR. So between two registers A, R naught, the value at A is B and the value at R naught is 21. So I think that's the next question. Yeah. So you have the question open. You can use the same. If you click when the presenter has gone to the next slide, I think you will be able to see it there itself. The question remains the same as what you saw on the simulation. So you have ORL A, R naught. R naught is 21 and A is B. So we have to find the answer for that. Okay, I'll wait for a couple of more answers before we look at the results. Okay, I have only one. Okay, please keep voting coming. I have 7 answers. I'll probably wait for till we reach 15, and then we'll look at the results. I have 8 answers on a class of 42 people. Okay, I hope that's all I will get. So I will go ahead and discuss the result. Okay, I think this answer is right. 0x2b is right and 0x21b is wrong. We will try to look at it from a calculator view and see what is going to happen. I'll clear the drawing so that it makes easier for me. So I'm going to do a bitwise operation called as OR between two variables, 21 hexadecimal 21 and the hexadecimal B. Okay. Okay, so we got 2B. So one way to look at it is that you do a bitwise OR of every bit and then take the result. I can do a demo of that. So we'll look at first hexadecimal 21. That is 00100001. So 00100001, and we know what a B is. 1011. So I'm going to do a bitwise OR of this. So bitwise OR doesn't have the concept of carry, so you can do it from both the sides. So 0, so you have to OR every bits vertically. So 0 or 0 is 0. 1 or 0 is 1. 0 or 0 is 0. 0 or 1 is 1. 0, 0, 1. 1 or with 1 is again 1. So you will get 0, 0, 1, 0, 1, 0, 1, 1. 1, 0, 1, 1 is B. This part is B. 0100 is 2. So this is 2 and this is B. So that's why we get the result as 2B. So it's a bitwise OR. So why it cannot? So you are not multiplexing anything here. So you will not get a result which is more than 8 bits. So if you look at this result 2 and B, it is actually 12 bits. So A register cannot hold a value of 12 bits. So that's why 2 and B is wrong. This is to help those who have answered 2 and B to understand why that is wrong. So we'll look at the demo. So 2 and you can see that it had 2 1 and AC had B. So now when I OR after the instruction 9 has executed, you can see that the answer is 2B, which is what we saw there as well. Okay, that's it. Okay, and then there is a special instruction called as X or L. Okay, I'll go to that quiz. So that XORL does an bitwise XOR of every register. So I have a question open for that. So you have a register A with the value F3. So you do an XOR of A with again A. Oh, this is an OR. So I think we'll go to the next question. Or we can first do the OR. So we'll answer this question first. This A is 0xF3. You do a bitwise OR of A with 0F. So now this is just a reinforcement of the previous concept which we studied. So we try to OR A F3 with F, and then we'll try to answer this. If you can answer this quickly, then we can go to the next question. So I think we are wasting a lot of time in waiting for responses. So if you can make the responses really quick, it's like you have to go to a website, think the answer for 10 seconds, and then click the answer. So I guess we shouldn't take anything more than a minute to answer this. So I will set a stopwatch at 60 seconds. So you'll probably see the time running. So we'll ensure that we don't spend anything more than 1 minute waiting for an answer to the question. So I can see that the time is 45. So you only have 45 seconds to answer this question, and after that the voting closes. It doesn't mean that you can live without answering that. I just want to make sure that we speak more. So I want you to answer the questions as quick as you can.
Students, give your responses fast.
Yes, thanks, ma'am. Okay, so I have 6 answers by that time. Okay, the voting is closed. I would that's so bad that I could only get 6 answers on this, but I would like to stick to the timing so that we can speak more. But I want everyone to answer. Going ahead, please ensure that you guys keep answering within the specified span of time. And I think the answer FF is right. 00 is wrong, and F3F is the same concept which we discussed already. That also wrong because the answer is greater than 8 bits, which the A register cannot store. And OR, unless both the operands are 0, an OR operation will not lead to 0. I think we'll quickly look at the bitwise operation of this as well, so that you guys get familiar with it. So I have FF just 1111, and 3 is 0 0 1 1, and then I OR it with 0 0 0 0 1 1 1 1. So if I OR, then this becomes 1 1 1 1 1 1 1 1. So that's why the answer is FFFF. So yeah, I think a lot of people have got it right. I like thanks for that. Okay, now this is the question which I wanted to start with. This is an XOR. XORL operation does an XOR of two values. So A has a value 35 and R naught has a value 35. Now we will try to XOR A comma R naught. I have a stopwatch running at uh, running for a minute. Yeah, thanks for answering. Please keep answering quickly. Please keep answering so that we have more stuff to discuss. Okay, so we have all the answers. I have extended the answering time by another minute on the hope that I will at least see 10 to 15 answers so that I have an basic explanation of what is happening. So the idea is that you need to work the answer out and then type it. So the more time you spend looking at what is the result, the more confidence it gives. Okay, I have another 20 seconds and I have 9 11 responses. So 10 seconds. 9 8 7 6 5 4. I think we are running down. Okay, thank you. Okay, I'll anyway open the answering so that you can keep the answers coming, but I will spend time to explain what the answer is. If someone wants to answer, you can go ahead and keep answering. The answer window is open again. Okay, so the answer is this is wrong. This is wrong. This is wrong as well. If you XOR a number with the same number, the answer is 0. So this is the answer for that. So I think again this is a basic math. So we will spend some time to look at why this is happening. So as you know, XOR has a formula of A bar B plus B bar A. You know, this is one of the universal gates as well. Is this one of the universal gates? Okay. No, I didn't get. Okay, I don't have a quiz, so it's very tough to answer that. So XOR is not a universal gate. I just wanted to, if it was a class, we could see some responses on the face. So I thought I'll see something there, but in a video it's tough. I can understand that. Okay, so when you do an XOR of A not B plus B not A, assuming that A is equal to B, what happens is it becomes A into not of A plus again A is, I'll replace B with A into not of A. So A into not of A, as you know, is always 0. A number with its complement is always 0, and again A into not A is again 0. So 0 plus 0 is again 0. So whenever you XOR a number with the same number, you will always get 0. This is one of an interesting property of the XOR gate. So this is always used to clear a register. If you don't know the content of the register, you can always copy that register to another place and then XOR it with that same register, so it will always go off. Or you can XOR the register with the same register again, then it will again go off. So that's one way to clear a register. So I thought that was an interesting question to ask. Mm, we'll go to the next set of instructions. We were at XOR gate before. Yeah, so what is special about XOR is the question. So now we know that when we XOR a number with the same number, we will get 0. We proved that property in a notepad file. Hope that's explanatory. The next question is this is a complement instruction. I'm drinking some water. So that's the noise which you hear probably. Okay, complement instruction tries to complement a value of the register. I don't think I have a question for it, so I will quickly explain what it does. A complement means it will complement the value. Complement of a number is the one which makes it complete. Complete value is like you make it full. So you would have read the complementary angles in algebra and geometry, where you want to find a complement of an angle, you find out the number which you have to add to it would make the degree 180 or something like that. So I'm not sure whether the complement is 90 or supplement is 180 or something like that, but that's the concept. So you want to find a number which makes it full. 180 degree is full in one sense. So similarly, a full value of a register is FF. So we find out the value which when added to the current number makes it FF. So how do you do that? You subtract the current number from FF and figure out what happens. So complement instruction pretty much does the same. So you could see that I have an value of 2B on the accumulator register, and I'm going to execute an instruction called as complement. So you could see that when I do when after the complement instruction is executed, the value of accumulator has become D4. In the previous slide, you could see that the value of the register is 2B. Now it has become D4. Why it has become D4 is we have subtracted FF minus 2B and the value is D4. So I hope I don't have a question on that. Yes, I don't have a question on that, so we don't have to spend time here on that as well. Okay, then we'll go to the next instruction, which I call, okay, the same instruction complement is called as CMA in 8085. Now I have a question like CMA of 0x55. What is the result? So we can work, since I don't have a quiz, we'll surely work it out. So 55 is the number, 0x55 is the number. So we want to complement it. So to find that, we will do on 0xFF minus 0x55. So if you do that, you will get 0xAA. I know I would, this looks too complicated to you. You might not be able to subtract hexadecimal numbers this quick. But once you are pretty much used to microcontrollers, you will be able to do that. We will see that. I will do this here. If I have a hexadecimal 55, I will subtract hexadecimal 55 from FF. FF is the full number, so FF minus 55. You can see that the value is AA. So that's what I was referring to here. One good thing about the number, you should look at the hexadecimal value of that, of the binary value of that as well. So if I write AA in binary, it is 10101010. Similarly, if I write 55 on binary, oh man, it is 01010101. So 01010101. Now you look at a complement, then you see wherever it is 1, it is now made 0. Wherever is 0, it is made 1. So that's one another way to look at complement. And this is AA and this is 55. Remember, all the numbers which I write are mostly hexadecimal, so I don't mark them hexadecimal explicitly. But for convenience, I think I can mark that as well. So one good thing about this pattern AA and 5 is that they have an alternating 1 and 0. So this is a very interesting number to send out on any IOs. If you want to configure an IO and check whether the IO is working, if you make it 0 or 1, you might always have a doubt whether it is working properly or not. Probably whether you put the oscilloscope at the correct place and all those questions. But if you make it a number like 5 or AA, you will know that it is always changing, like 1 0 1 0 1 0. So that's an alternating pattern. If you look at it, it's a square wave. So that way you always get a confidence that it is continuously changing, and it is easy to probe and confirm that. So that's why AA and AA and 5 are two interesting and important numbers when you have to work with microcontrollers. I hope you can understand that AA and 5 are a square wave. Like if I don't know, it's not that easy to draw a square wave in this, but nevertheless I will give it a try. Yeah, so this is how it will. If I draw 1 1 0 0 0 like this is how the wave will look like. So now it is 1, and then here it is 0, here it is 1, here it is 0. So this is how the wave will eventually look like. So that's what we do with ones and zeros in microcontrollers. Okay, then I have an instruction called as rotate, which is going to rotate a number. You have a number, you assume it as bitwise, and then you rotate it. You whatever is on the 8th position, you make it 7. Whatever is on 7th position, you make it 6. Likewise, you shift it to the right by 1, or you shift it to the left by 1. So we call it rotate through accumulator right. You can call it as right shift as well. For an easy understanding, it's a right shift and left shift. So that's probably the next question I have. So you have a number 6A in this register. We have another 12 minutes. So we have a number called a 6A in this register. Now I am going to rotate it through right. So you could see that after rotate, it becomes 3 5, and then it becomes 3 5. So I'll execute it for a couple of more times, and then we will see what is happening there, and then we will try to see if we can make a generalized assumption of what is happening there. So I'll put in a value like 80, then we will run it. So okay, it got reset. So I will make ACS 80 as now. Now I'll step through it. You can see that after a rotation, it becomes 40, and then after rotation, ACS become 20. After rotation, ACS become 10. After rotation, something is happening again. So that opens up to the next question. I hope you can see the question. A is 0x6a, and then after you rotate it, it becomes 3 5, and then after you rotate it, it becomes 1a. So the question is, what is a doing? What is the rotate operation doing? You can guess based on the results what it is doing, and then try to make a generalized assumption of what a rotate instruction is capable of doing. Please go to this menti.com and type 23923 to answer this question. I will start the timer anyway and see if we can get it answered in 1 second. You can see the timer is running. Okay. I have one answer. I'll keep the answer. Yeah, so and I think we have some more time. Have 30 seconds more to vote. Okay, I think the answering got closed. I will open it up for another minute, so I will keep the answers coming in. But in the meantime, we can discuss the answers. Okay, so 5 is a very less number for me to make a generalized assumption, but I will go ahead with what I have. So okay, this is partially correct. It is, yes, of course, it's removing the LSB, but I wanted a very deep understanding of what what a rotate will do. I tried to steer you away from looking at the number as a decimal number, just on the hope that you will get confused. But I on but I also want you to think on a hexadecimal perspective to see what is happening to a number. So this answer multiplying by 2 is again wrong. So divide by 2 is right. So we will try to look at it from an decimal perspective on this calculator, and then see how it makes sense as a division, and then we will try to come back to hexadecimal and then see what's happening. So there is an arithmetic logic shift here. So I will take the same value 80 in hexadecimal. That takes a number 128. We'll shift it to the right by right shift. I'll right shift by 1. The number was previously 128. We look at it on a decimal, it becomes 64, and then I'll do another right shift by 1. Whatever was 64 has now become 32, and then I do another right shift. 32 becomes 16, and then I do another right shift. 16 becomes 8. So that then if you look at it on a decimal perspective, I think it is very obvious that it's a division. So we'll try to look at it from an binary perspective as well. So you know what an 128 is? 0 1 0 0 0 0 0 0. Let's take a number like this. This is 128. If this is not 128, then I think that's a problem. So 1 2 3 4 5. Okay, I'll do decimal 128 and see. Okay, I have another 0 extra. Okay, this is 128. So what happens now is when I rotate it through right once, the 1 gets shifted here. So this is the rotate. So when I rotate it by 1, first thing obvious is that the decimal position is changing. Like if you count money, if you just do our number system like ones, tens and hundreds, we have hundreds, tens and ones. Sorry, this probably looks like some second standard, third standard kids textbook. So if you have a number in the hundreds place, that's like 100 rupees, and then I shift that to the 10th place. I just shift the number by 1. Then you see that this number is 100 rupees, and and this is 10 rupees. So you can see that the value of the number has reduced by your if you rotate it by 1. So that's as good as division. So if you look at a decimal number, then this is how do you get 100 to 10. So every time you shift it there in a decimal number system, rotate in a decimal number system, just divide by 10. So the number was previously 100. Then if you rotate it to one place, then it becomes 10. If you rotate it by one more time, it has become 1. So that's as good as dividing this by 10 again. So it was 100, divided by 10 is 10, divided by 10 is 1. So similarly, in a binary number system, if you rotate, now you have a binary number system because you are rotating it by 1 bit. Because it's being rotated by a bit. Even though we look at the number in hexadecimal or decimal or whatever equivalent, what we are doing is rotate by a bit. A bit is a binary equivalent. So when you rotate it by 1, this has become now 64. And then if you rotate it by another 1, so that has become 32. That becomes 16. That becomes 8. That becomes 4. That becomes 2. And that becomes 1. So this is how you look at the number on a binary perspective. I hope the text is visible. Well, anyway, for the sake of it, increase the font size a bit. Okay, I just did a number system equivalent to convert every number back to decimal, and then and of course this answer removing the LSB is actually right. It's not dreadfully wrong. Multiplying by 2 is mostly wrong because when you rotate it through the right, you are dividing by 10. So dividing by whatever is the number system which you are using. If it is a decimal number system, you divide by 10. If it is a hexadecimal number system, you divide it by 16. But if it is an binary number system, you divide it by 1, divided by 2. So the answer is divide by 2, which is what only 2 people have answered. But I hope I could explain and correct your understanding on that. I can go to the next slide and see what is there in that, and then plan accordingly. Okay, so we looked at what rotate does. Okay, so the next question will be what a rotate through left will do. I think, yeah, we will spend some time and close this with that. So we will use the same graph to explain what happens a rotate by left will do. So we have a number which is 1. So if you rotate it by left, the position of the 1 from the first bit has gone to the second bit, which means that the positional value of the number is getting increased. So that's equivalent of getting the number multiplied by 2. So for instance, if I go this table from bottom up like this, if I want to go at it like this, I don't know how I will do that. Yeah, I want to go to the number like this. It goes up. So you could see that the positional value is getting incremented, and then the number gets multiplied. So it's as good as here. So you have a 1 rupee, and then when you left shift it by 1, the positional value of 1 has become 10. So that is equivalent to having 10 rupees. So you can see that the value has increased. If you rotate it through left by one more, it has become 100. So the value is getting increased. So that's the next question. So when you rotate through the left, it is getting multiplied. So one significant advantage of this is that if you want to divide by 8, I think probably that's the next question. Okay, this question is a rotation with carry. For want of time, I will try to refrain from asking that question. Okay, that's mostly on jump. Okay, yeah, we'll try not to, we don't have to discuss that question now. So all I wanted to say with this was that when you rotate through left, the positional value gets incremented. And then the next thing which I wanted to ask was rotate with carry. So meaning that you rotate the number with the carry. So whatever is on the carry comes to the 0th bit, or whatever is in the carry goes to the most significant bit. That's the next question, but I think we don't have to really look at it now. I'm going to close the class for the day. It's 4 now. So if you have any questions, we'll wait for some time. Let's say we'll spend a few minutes to discuss. If you have any questions, anything which you want to specifically do on the last class, which is tomorrow, and things like that, so that we can reach the conclusion for the day. We'll open it up for questions.
Students, if you have any questions, you kindly ask now. I think you have clearly explained all the concepts, so that's why the students don't have any doubts, it seems.
That's a positive way to look at it.
Okay, sir. Thank you for your clear and explanatory session, sir. I hope you to have the same session tomorrow also, sir.
Oh, yes, ma'am. Okay.
Okay, sir. Thank you, sir. Thank you very much.
Bye.
Bye.